assistant research scientist at the University of Michigan. He has received his bachelor's degree in nuclear engineering from Cornell University in 2006, master's degree from University of California, Berkeley in 2008, and he was also a Brownfield Campaign Initiative Fellow. Then he received PhD from University of Michigan in 2013 with support of the CASL program. And as a PhD student, he was the first recipient of the CASL Knight Award for Technical Contributor of the Year. And since then, he has played a key role in the CASL activities. Please join me in welcoming Dr. Kochunas.
All right, good afternoon, everybody. I was advised to point out, for those of you who weren't aware, but Michigan gave quite the trouncing to UNC in college basketball last night. And so I think we're all very happy about that. Today in my lecture, I'm going to talk about some of my research activities and a lot of things that have come out of that. And in particular, I want to relate those research activities to a course I developed at the University of Michigan. So the outline for my talk, basically, I'm going to start with some motivation, in particular, give you just a little bit of background on the CASL project. NC State's been a part of CASL since the beginning. A lot of you are probably very familiar with this, but I'm going to assume that maybe a few of you aren't. And then, from there, I'm going to just sort of lay out what I mean when I'm referring to computational science and engineering. After that, we'll kind of, by example, go through the story of MPACT and how that is sort of a computational science and engineering success. And sort of how those experiences led to a course I'm going to talk about called Methods and Practice of Scientific Computing. And lastly, I'll finish up with some MPACT has contributed to within the CASL program and some of my activities over the last year or so. So for those of you who don't know, CASL is a big consortium that was $125 million for 5 years. We're now in year 8, I think, out of 10. And this was sort of the first energy innovation hub. NC State, Michigan were founding partners, and their sort of charter goal from the beginning was to develop advanced modeling and simulation tools to be applied to the light water reactor community, and sort of in particularly the pressurized water reactor community. And they wanted to do this by engaging members of the university, the industry, and also the national labs, and try and develop new collaborations and partnerships and ways of technical people working together to solve big problems. More to the point, what we're kind of interested in the nuclear engineering aspect, and myself in particular, is solving the transport equation. So I'm somewhat of a transport guy, like some of the faculty here in the department, so I'm not allowed to give a talk without showing the transport equation. And then, what are we solving it for? We're solving it for light water reactors, okay? So, the department here, I think, has pretty strong collaborations with industry, so hopefully most of you have seen this technology before in some of your courses. By the way, that sounds sort of easy if you lay it out on one slide, but there's a lot of complicated operation. These are real machines, very complex machines that we've managed to build and operate. And so we can be very good at solving a fundamental equation, but doing things to sort of simulate operation is another challenge, right? We're throwing in this human component that's very unpredictable and kind of just a nightmare to deal with from a programming perspective. But reactors can operate up and down in power, especially in the first cycle, as we're seeing here with Bar Unit 1. They have detectors everywhere, and all these things need to be accounted for when we're solving the transport equation. And by the way, they asked us to do it on some of the nation's largest supercomputers. But really, the industry partners within CASL kind of pushed back, and they said, well, actually, we'd actually like to just be able to run this on 1,000 cores. We don't have, one of the top 500 supercomputers in the world. So, spoiler alert, CASL's in its 8th year, must have done something right. I think the big success in the first 5 years was kind of culminated was the simulation of 12 cycles of Watts bar unit 1, multi simulation, showing you the end of cycle pinwise exposures. This is not something you get from the traditional methods, and being able to shuffle those around, a detailed picture of what's in the reactor for sort of the life of the reactor that you're interested in. So, kind of what this talk is about is how was this accomplished? Like, how did all of these people come together, manage to do this, and, in particularly, sort of what were the roles of the people working on MPACT and myself? We start from a transport equation and a given problem, and we end up with this nice solution at the end. So this is just a boring video. This is just the cycle 1 depletion. But does anyone want to offer a thought about, what goes in this big question mark box? It's okay if nobody does. That's fine. Okay, so computational science and engineering, right? So this is, again, part of this talk. So what do I mean when I say computational science and engineering? This is sort of at a very high level in terms of science. It's an emerging multidisciplinary field. It's the intersection of computer science, science and engineering, math and statistics. And smart people can spend their whole careers in just one of these fields and accomplish something worthwhile. Having a single person do all three is astounding. But having someone being competent or advanced and not necessarily a world expert is sort of what you're trying to accomplish with computational science and engineering. We're engineers, and so how do we participate sort of in this paradigm of doing research? Well, we're engineers, so that sort of implies that we have an existing technology that we're working with, that we're interested in, and we sort of understand from that our governing equations in physics, what's in our system. But, again, we're not at the forefront of the fields of computer science and mathematics necessarily. But, these are things that we want to use and utilize effectively, in particular on computers. So, this brings me to another point. This model, the way that people think about this, they talk about it as the pillars of science. Why so much focus on this computational science and engineering? The traditional scientific and engineering method, was theory. You start with pencil and paper. You're Enrico Fermi under Stagfield, doing calculations that are matching the counter for Chicago Pi 01, right? It's all pencil and paper. I guess in the other room, though, you do have experiment. And early on, this was really what people were using to design the reactors that we still have operating today. You build experiments, you build prototypes, all of that. So this approach has limitations, though, right? In general, things can be too difficult, right? If you want to get flow patterns of a 747, are you really going to build a wind tunnel that's that big? Probably not. It could be too expensive. Sticking with our airplane model, you can't just, if you want to see how an airplane is going to crash, you don't want to just go crash an airplane after you build it. It could be too dangerous in terms of nuclear weapons. This was something we saw with the Nuclear Weapons Test Ban Treaty back, I think, in the 90s, in the formation of the ASCII program. You went from experiment to basically simulation. And there are other phenomena, climate change, astral evolution, that are just too long for one human to observe through experimentation to develop new theory. So this is the role that simulation is serving in the area of science, right? We're going to use computers. This is a relatively recent tool that we have, and we're going to do science. So stand back, everybody. We're going to do science. So briefly, my background in this, coming from Michigan. Michigan has a computational and science engineering institute called MPACT. Again, it's all the things I've said. It's interdisciplinary. It's fairly recent. And it's been a mechanism for the university to sort of foster research in this area and do different things, offer educational opportunities. We offer PhDs in scientific computing or graduate certificates. They hold an annual symposium and get some pretty cool papers. They also have seminar series, faculty workshops, etc. And they've also sponsored the development of a few courses, in particular the one I'm going to talk about that I'm responsible for. But they've had a few others that they're working on. So in this context, what we're doing in this course, it's a multidisciplinary field, and this creates some challenges. And I'm not aware of too many other places that are trying to develop a course like this. And so in some sense, I would say academic institutions are still trying to figure out how to do this. And in my experience, it's a difficult thing to figure out how to develop the material and teach the material such that everyone's sort of getting the same value out of it. The question you kind of have to start from is, what are the important topics for engineers to be effective computational scientists? So, basically you're coming into this world as an engineer that wants to solve a problem, but you're kind of interested or particularly skilled at using a computer. So, to answer this question, what's going to be helpful for them to learn, it's good to start from, case studies or use cases that have been successful. And, that gives you some information about what to put into the course, but then, there's always this other pesky aspect of how do you teach these topics. And one way is to find a gullible research scientist to overcommit themselves, a couple very talented GSIs, and then hope for the best. So as our use case, of a successful computational science and engineering story, I'm going to talk about MPACT, which is the deterministic reactor physics code for CASL. So, a few high-level details about MPACT. It was not something that existed at the start of CASL. It was something that grew out of the program. For CASL, they want it to be a production tool that's easy to use and providing value to the industry. And the way it's going to do that is, through pin-resolved power distributions in the reactor. And so it's kind of this piece that sits at the heart of the core simulator. To academic institutions, that we're a part of, MPACT, we want this to be a research tool, a research platform. You have experimentalists that have their labs with their apparatus. You've got the Pulsar reactor. These are all experimental apparatus that enable research. And this is how we want to think of MPACT, except being a real thing, it's just source code. And this is going to let us do PhD research in several neat areas, and also as a teaching tool. The algorithms in here, some of them are very well established in our field, and if you're going to be a user of these tools, it's always better to be a smart user than a dumb user, so the more you can learn, the better. And so we can use it as a teaching tool. Overall, CASL's main product is this thing called Vera, and even today I hear people say, I still don't understand what Vera is. But for the purposes of this seminar, this is Vera here. In particular, we're going to focus on the core simulator, which is input and output processing, thermal hydraulics, so Cobra TF, which is developed in state, and then the neutronics aspect, which is MPACT, and then now both of these codes are sort of relying on general scientific software libraries to efficiently on these large computers. So that's kind of where it sits in the overall framework of the CASL program. So how did it get there? So starting out, this was really a bunch of code I was working on in my PhD dissertation back in 2011. Developed all of these different parts, and after 6 months or so, we got a visiting student who came in and was going to work on this with me. And then after about another semester of that, I can't, at this point I don't quite remember what happened, but other grad students started getting excited about this, and other people wanted to begin contributing to it and working on it. And so now our team is growing, to probably half a dozen people at this point. And then after a year or so, we finally came up with the name MPACT. And for the next 2 years, all of us were working pretty aggressively to develop all the capabilities that were going to be needed to help solve the problems that CASL was interested in. And then, we started to put together some of our first publications back at the M&C 2013 meeting. And then after a lot more hard work by a lot of people, not just myself, CASL decided to make MPACT its primary pin-resolved neutronics tool. And so this was, back in those days at CASL, maybe a hot button issue. I'm just a lowly grad student, so I don't have to worry about that too much. I just like to sit there at my computer and code. But we were competing against some of the best tools that Oak Ridge had to offer. Adopting it, MPACT becomes co-developed now by Oak Ridge and University of Michigan, and a lot of our former students have gone on to Oak Ridge and are still doing a lot of great work in MPACT. And then shortly thereafter, we met our metric of success within CASL, and it was renewed for another 5 years. So, the early years of development, I'm going to kind of walk through this now in detail, and then relate what was going on with the computational science and engineering topics, and we'll sort of follow how this builds into a syllabus for a course. So, back in April 2011, again, this is where we are on the timeline. We're already a year within CASL, and at this point, we'd been exposed to what the labs were doing in terms of computational science and engineering. And the key activity that we took away from this interaction was, laying a good foundation. So step one is you find a gullible graduate student that doesn't mind adding a year to their PhD, and then you spend a lot of time putting conscious thought and effort into practicing these concepts. So what are these concepts I keep referring to? The first one is version control, and this is paramount. Right? For the computational scientist, version control is basically your laboratory notebook. It's a record of everything you've done in terms of setting up your experiment, and what was going on and what changes were made. It's actually slightly different in that it doesn't really contain results. But this is crucial in scientific software to be able to have reproducible methods reproducible results. And of course, this is something that is fundamental to the scientific method. You think about what we're trying to do with science, it's good every now and then to go back to the basics and remind yourself of the simple things that you're trying to do. Reproducible results, the foundations of the scientific method, one of those. It's also indispensable for collaboration. You can explicitly refer to the different versions that someone's working with, and all of the changes sort of happen in a straightforward manner. And when two people change the same thing, right away. Testing is the other essential piece, right? So how do you know your code is right or working? And if you're going to touch someone else's code, how do you know you don't break it? That's what testing is for. It's extremely useful in any software project with more than one person. But I'll argue if you're the only person writing the code, it's still useful for you if you plan on working with this code in the future, because you will forget eventually what you were doing before in that code. So, outcomes. Another one is, those are some of the activities. Another thing that we sort of learned and adopted was this concept of a life cycle. So every bit of software has a life cycle. It might be implicit or it might be explicitly defined. And what we realized is we can explicitly define this thing. And there have been some very, I think, smart people thinking about this problem from Sandia. Find a way to have a process that meets the goals of what you want your code to be, right? So CASL wants a production tool. At a university would like a research tool. And those are two competing modes of working. So how do you handle that? And one way to do that is to make sure you have different maturity classifications of your code. But more importantly, it's build quality on top of quality. And so what's illustrated in these figures here, sort of qualitatively, are different metrics related to maturity And in looking at it, you can kind of see what activities you should be doing in terms of working with the code through different stages of that level of maturity. So, some of the things I just want to highlight, for research stable code, this is code you're going to publish. Reproduce basic unit testing and verification. Very beginning. Very hard to go back and sort of put in the effort to add this. Acceptance testing, what does it need to do for the user? That's something you do later. At the research stage, you're just trying to figure things out, see if the idea that you're working with is going to be valuable, is going to pan out. Right, acceptance testing, not so important. Documentation and tutorials is not so important. Again, at the early stage, you might be the only user of this. It doesn't need to be robust. It just needs to work for you so you can write your publication. Another one that's important from the beginning, code design and clarity. So, you should anticipate that your code is going to need to do something different. And you should think about that consciously when you're trying to design it so that it's easy to change in the future. This is what enables you to rapidly prototype things down the road and have a software system and research platform that's sort of easily modified. In terms of supporting users and backwards compatibility, those things, these are all activities that you do sort of later once the methods are established. And I can say, from my point of view, this is sort of more or less how things evolved within CASL in terms of working with MPACT. This is more or less how our activities have gone over the last 8 years, 7 years, 5 years. Okay. Right, so the growth period where we had a lot of people working on the code, a lot of people working together. Version control helps enable this. We have good testing so we can be confident that we're changing each other's code without breaking it. Allowing conscious design also gives us a way to sort of divide up the work along logical boundaries that allow team members to work in parallel and contribute to a final result in a shorter amount of time. Right, so our CSE topics are, we're kind of stating the obvious here, but software design. And as I mentioned on the previous slide, well-designed software basically means it's easy to rapidly prototype something. And it's a very difficult skill to learn, and I think it's also a difficult one to teach. It really requires, in Bloom's taxonomy of understanding, it's like that final level of synthesis where you're actually able to internalize and understand the underlying theory so that you can go in and apply it in new ways. It really requires almost that you spend a lot of time doing it the wrong way to understand that there's a better way of doing it. And then the other one is development process. And so if you have a lot of people working on something, it's easy for things to get chaotic. And having a process is a way of managing your chaos. And forces good habits. So you sort of add these routine activities, and people kind of learn what the next steps are, and everything kind of becomes a routine process that helps everything move faster. The downside of this is it's hard to enforce. You kind of have to just self-enforce. And when you stop doing that, or if you don't have the self-discipline for it, then it will break down, and it'll lead to problems. So that's sort of what it takes to do that. And I'm not sure there's a better way, but automating the enforcement would be best. In some cases, you can do that, and for other things, not so much. So this is what our development process looks like. This is maybe a fun topic for computer scientists. And the general advice is find out what works best for your project. And this is what we found works best for ours. And I would say in medium to large-sized research software projects, if it's just you and it's some toy code or research code or code for a class, this is overkill. You're going to spend too much time thinking about how to solve the problem rather than solving the problem. But what you want to do is you want to have requirements, and then once you understand the problem that you're supposed to solve, you can begin figuring out how to solve it. From there, you want to design the overall system. how all the pieces are going to fit together. And then you move into this high-level design. And one thing that you have to account for is that your requirements are always going to change. So this whole process becomes iterative. Once you think you have an outline of what the code should be, this is really just outlining. So if you're writing a book, this is kind of going through the different chapters, and then this might be sections within those chapters or something like that. It's kind of the notion you're working with. But it's really all down here. The software, actually sit at the computer and type out the software or the source code. Your low-level design is just sort of between the start and end of your subroutine or function. And it's a good idea to write tests for what that subroutine or function should do before you actually write it. And that sort of lets you know when it's complete. It's a way of reinforcing your requirements. So I mentioned, the other one was our outcomes were a process, which we just went through, and then also software design. And so this is somewhat out-of-date picture, but part of the design of the software. And the logic here should be pretty obvious. It's basically look before you leap, right? Software, oftentimes in science, will evolve into a complex system. And with complex systems, they require design and planning, right? You're not just going to go build a nuclear reactor grabbing some tubes of zircaloy and some pellets of uranium and just start welding, right? You're actually going to sit down and figure out what you want it to look like, or if you're building a house or whatever, or that's kind of what it's going to be. You should have a plan, and understand that what you're trying to accomplish is going to be complex, and it facilitates coordination. Okay, so I mentioned a while back, in the timeline, so this last part was we had this bake-off in CASL, sort of how people talk about it now, but there were these series of progression problems that individuals in CASL came up with to sort of drive the requirements. What do we need the code to do? We need to solve these problems. And so these problems are increasing in complexity, and our first 5 years in CASL was basically developing the capability to get to the bottom of this list here. And so these are some of the CASL report numbers where we were able to check off, like, we solved this progression problem. And somewhere in here, I think, was where the decision was made to go with MPACT. So at the beginning, I mentioned we started with testing kind of the outcome of that through the very end. This is still some time ago. But metrics here are kind of fuzzy. The metrics I'm showing aren't always the greatest, but they're helpful. And so this metric here is just the number of lines of source code. So this is during our growth period. We can really see that we're adding a lot of source. This is over a 5-month period. So we basically doubled everything. But along the way, you look at the number of lines per line of source code, and we want these other ones. So test code per line of source code. We're sitting here around 7 or 8 lines. So for every 10 functional lines of source, we've got about 7 lines related to testing. And for those same 10 lines of source code, we've got between 4 and 5 comments, which probably seems a little excessive now that I'm looking at that. I'm sure it's gone down, actually. Yeah, and so the other metric you can look at that you can sort of look at uniformly across software, it doesn't tell you the whole picture, but it gives you something, is the amount of coverage. So we have all these tests. Are we actually testing the code that we've written? And this is kind of what that coverage looks like. So we 70, 75%, 80% over here, not bad. And then over here is sort of an earlier version of requirements testing. So we have these sort of loose notions of requirements, and then in this table, where there's an X, we can point to a test and say this test is testing this requirement. When this test passes, we know this thing works. But we haven't done a great job of that, and so this is actually one of our activities that we're working on this year. Right. So getting back to the course, right? That was sort of our case study. We went through the evolution of this code. We related that to the activities in the research project, to computational science and engineering topics. And so now, how does that inform a course? My sort of vision for this was, I wanted to take my experience and do something to enable that for other students. So what I want the students to be able to do is what I was a part of, which is produce software in their research that can eventually grow into high quality software. Have code get used at national labs, or in industry, or in the open source community. Whatever's going to work for your application. So what this means is, this is a slide I give my students at the beginning of every semester. Is these are the things you have to learn, right? You have to learn best practices in software engineering. You have to learn how to optimize code, how to use HPC resources. What are the tools that are available? You don't want to go reinvent the wheel. And overall, kind of all the various things you can do to be a more productive programmer or a better computational scientist. So this was the original syllabus I came up with. It's largely unchanged at this point. Some things have shifted around, but otherwise this is kind of what it looks like. So the course was 2 90-minute our computing lab. And so I'm just going to highlight again the relationship of what we were doing in our research and how that enabled success within the CASL project. And here it is. I can point to the syllabus, right? So early on, we look at some activities that facilitate a lot of people working together on a software project. More, 2 heads are better than 1. 5 programmers are better than 1, typically. Facilitating, this aspect here, workflows or good development processes, is something that enables us to reach our PhD goals and also the goals of the CASL project. And then lastly, testing down here, right? I don't think if we didn't have a strong testing base from the beginning, our code really wouldn't have been considered for CASL for long term. The other thing I want to point out is, it's really a crash course. In this first week, so we do an introduction and then we have the Labor Day weekend. But then in the first week, we cover C, C++, Fortran, Bash, Python, and I've also added LaTeX in here. So it's like 7 languages in 2 weeks. So they're all multilingual by the end. All right, so that was the first half. The second half, so this is kind of where we are now. Move into how to understand how your code is going to run on a computer. Generally, this isn't a problem you should have to worry about, but unfortunately, it's a problem you do have to worry about. Eventually, 5-10 years now, compilers and other things, programming languages, might become advanced enough that we won't have to teach this anymore. But basically, you want your solution as quickly as possible. You have to understand how it runs on the computer. And so, I teach them how to model performance on serial and parallel architecture, measure things, and then how they can optimize it. Then we give a little crash course in parallel computing, debugging, and other libraries, other tools available to them. And somewhat recent, this is now, I guess, a year or 2 old, highlighting here the performance improvements we had. And I guess the other thing I want to point out, because I'm not recalling if I have it on a later slide, but they have a course project and project presentations at the end. And I encourage all of them to take typically about 3 ideas from the syllabus and apply them in their research code, and that is their project. So I get them focused on doing their research for course credit, which I've received feedback from the students basically saying they love that. The other thing I tell them at the beginning, is, this is a new course. Please bear with us. We're now in the 3rd year, so we're a little more comfortable, but be prepared to learn. And so here are our expectations explicitly. How to figure things out for yourself. This is an invaluable skill for a researcher. If you don't know how to do that, you may not go far in life. I'm sorry to say. So make sure you know how to do that. How to program in different languages. certainly you'll have your favorite, but if you're able to pick up more than one, that makes you more valuable. And at some point, you know, if they have a career here, they will work in another language. So I'm just getting it, exposing them to it early. I don't accept anything in MATLAB for a final grade. And then, you know, I tell them, expect to learn about a lot of things. Several, if not all of these topics deserve their own semester-long course. And to be able to distill that down into a single lecture is pretty challenging. And especially convey the main teaching points, valuable information that they should learn from that. But if they're familiar with it, also enable them to have some depth. So, you know, the promise I make to my students is that by the end, that they're going to be a jack or Jill of all trades, a master of none, and in particular, you know, they'll know just enough to be dangerous, but not enough to be competent. They'll know enough to how to crash a supercomputer, but not how to use it effectively. They'll need a little more practice for that. So, you know, some things I think are interesting and fun about this course is the variety of students that I get. So for the past few years, this is kind of what this looks like. You know, I get students from all over engineering. I get them in math, chemistry. Because this is a new course, we teach it as a special topic in nuclear engineering. So the nuclear engineers are really good at finding it. Students outside of that struggle a little more. But it's a lot of fun for me to be able to see the other problems that students are working on. It's a nice way to get exposed to new ideas. And also give them new ideas. You know, some of the things I talked about in terms of what we practiced in our software project of MPACT within the context of CASL, and the CSE topics that we were applying and how that fed into the course. You know, I also give them a survey to just find out how much of this do they already know. And it turns out, you know, that basically there's a need for the things I'm teaching, right? Barely anyone in my course, I know who these 6 students are because they're my students, have written a unit test. And this is sort of, you know, critical in any large software project. If you want them to write meaningful software that's going to be used by someone other than them, it's really a necessity. Version control, you know, about half. And then, you know, how many of them have actually worked on a software project with more than one person? And it's very few. And so this is something that I, you know, encourage in the assignments. So that kind of wraps up the part where, you know, I cover experiences with MPACT and how that led to this course that's been a lot of fun. So, you know, we're going to switch back now to kind of the nuclear engineering mode and talk about, you know, all these things we were doing with MPACT and all of the, I'll call them successes, that have been enabled by the fact that, or the virtue that MPACT exists within CASL and does what it needs to do well enough. You know, me coming from a university, we like the David and Goliath university versus the lab. You know, and certainly this has been good. You know, if we didn't start throwing in our resources together on this, we certainly wouldn't have accomplished everything. We couldn't have continued the pace that we were going at. But, you know, I mentioned earlier, there's been, you know, successful simulation of 12 cycles of Watts bar. I think they've done several more since. Successful prediction of the Watts bar Unit 2 startup, also the AP1000 startup over in China. Westinghouse has also used MPACT for VRCS. I should give more credit to the CTF's contributions here. But the reactivity insertion accidents of the AP1000, and I was talking with someone else within CASL earlier this fall, and I think they mentioned there's now like something like over 100 cycles of operation that the code has been used to model. Which, as I say, it seems a little high, but that's the number I'm recalling. So there's lots of different, you know, industry institutions, international partners that are sort of interested in what we're doing. And it's really cool to see this, to you know, have been a part of this. You know, I mentioned sort of somewhat recent successes. So, you know, recent was 2016, but we were able to speed up the code, considerably across several different areas by, specifically targeting them. So, a lot of these early milestones, we just need to get the capability in there. It didn't need to be fast. And then we did a lot of work to speed things up. And so you can kind of see that here on this graph, where basically these different bars represent the time spent in different parts of the code, and we're just sort of systematically reducing them over, this was maybe close to an 8-month period, I think February to August. Right, so some recent applications. The one I've been most involved with has been the reactivity insertion accident. So for those of you who aren't aware of what that is, this is just a little bit of a background. But it's basically one of the most severe postulated accidents for a light water reactor. It's a design basis accident. It's required by the Code of Federal Regulations that to license a reactor, you have to provide evidence that your design will not result in damage to the coolant pressure boundary, greater than or limited, to local yielding, impairment of core coolability. This is this has been around for a long time. There was back in 1974, they had to come up with some criteria that'd be uniform for everybody, and what they came up with was basically, during this transient, I think I ran out of pointer juice here. That's all right, I'm tall. So early on, they estimated about 280 calories per gram energy deposition in the fuel during this transient was, if you were under that, you weren't going to fail your fuel. But more recently, through some experiments over in France, they actually found that the number's substantially lower than that. And so over the past couple of years, the NRC has been drafting new regulatory guidelines about what the acceptance criteria for this accident are. So it's sort of reappearing with interest, and this is sort of the relevancy of why we're looking at this problem. Oh, okay, this still works. All right, so the RA from CASL's point of view, this compared to steady state, which up until the time was primarily running full cores. We'll see here in a couple slides. It's a very asymmetric accident, and VIRA, not necessarily within MPACT. An example of that would be something in CTF.
So it's not direct coupling, but
No, but you guys work on the coupling between
Coupling.
MPACT and CTF, right?
Yeah, we have. Yeah. You had a uncertainty. The sources of uncertainty in the RIA calculation, or just in general. Nuclear data is one. And then also I would say the geometric description. It's kind of the typical things of what goes into your computational model where you have to make approximations or assumptions. I know that recently with I think the NDEF 7.0 library, they didn't do some good things with the kinetics data, and people have been able to show that. And so they fixed it in 7.1, and it was fine in 6, and it's fine in the other nuclear data libraries. But yeah, I think it's kind of the usual culprits for sources of uncertainty. I wouldn't say that there's too much from the numerical methods or the discretization.
These are pretty small in this methodology, numerical reaction.
Yes.
Right.
Yeah.
But nuclear data, and you mentioned cross-sectional uncertainty, and now Oak Ridge and University of Illinois, Tomasz Kozlowski, they developed evaluation of kinetic parameter uncertainty.
Oh, they did?
They did.
I didn't know that.
It's a new one, which now can be propagated to the corporation.
Okay, that's very interesting. Yeah.
And this is part of this like water OIM benchmark.
Okay. Part of UAM?
Yes.
Ah, very good. Yeah. Sorry, we can take more questions.
Yes. And we welcome Vera CS participation in the benchmark. That will be very valuable.
Yeah, I think so.
Other comments or questions?
Your course, do you share it?
Not really. Otherwise, the university can't charge the students for material. But I can certainly, a lot of it, in particular things I'm less well versed in that I have to try and teach. I go find open resources. But certainly I can suggest books and other workshops, summer camps, things like that, where you can learn a lot of the same things.
Other questions? Let's thank the speaker again.
All right, I want to announce the winner of the chili cook-off.
Oh man, that's why everyone stuck around.
Spot who made the most money if y'all didn't get what we were doing out there. And all the money will be donated